Hello, everyone. I'm Yuqi Gu from the Department of Statistics at Columbia University. Today, I'm happy to present my work at Bernoulli IMS 10th World Congress. I'm going to talk about Bayesian pyramids, identifying interpretable discrete latent structures from discrete data. This is based on joint work with David Johnson. You can find our archive preprint through this link. I want to introduce our models in the broad family of latent variable models. This family can be basically categorized into 4 types based on the nature of the latent and the observed variables. For example, the popular factor analysis model uses continuous latent variables to model continuous observations. In this work, we focus on using categorical latent structure to model multivariate categorical data. Traditionally, the latent class model in the literature is a canonical example. It uses a unidimensional latent variable to explain the dependence of multiple categorical responses. But modern applications require more flexible and complicated tools. For example, in some applications, it is desirable to model the latent constructs as multidimensional to capture the fine-grained latent information. And it is sometimes useful to impose a sparse graphical dependence between the observed and the latent variables. Further, we also hope to model the deep structure of latent variables in order to extract the hierarchical and principled information. Combining all these motivations, in this work, we propose the Bayesian pyramids, a probabilistic graphical model for multivariate categorical data. The research questions we address are twofold: theoretical identifiability issue and the estimation methodology. Let's first look at the theoretical identifiability issue. When and what discrete latent structure can lead to model identifiability? Identifiability basically means, based on the observed variables alone, we can recover uniquely the underlying model parameters. It is a fundamental prerequisite for valid statistical inference. In our paper, we started with a unidimensional latent variable, proposed a constrained latent class model, and studied its identifiability first. But in the interest of time in this talk, I will directly go to the Bayesian pyramids, which are the deep, structured, and graphical extensions of the constrained latent class model. Here is a general formulation of Bayesian pyramid. The distribution of each variable depends only on its parents. For example, the observed variable y1, it has a parent alpha1 in the first latent layer. So for each subject, what we observe are its p-dimensional observed categorical responses on the bottom, and all the upper layers are latent. So the parents of all the yj's are specified by the red edges. And equivalently, we can see that these red edges can be summarized as a binary graphical matrix containing p rows and k1 columns. And its entries are binary indicators of whether yj has a parent alpha k. In a similar fashion, we can also summarize the parent-child information between the upper consecutive layers using additional graphical matrices. For example, these blue edges from the second latent layer to the first latent layer can be summarized by a K1 by K2 graphical matrix. Following the convention in the probabilistic graphical model, the conditional distribution of these observed variables given the first latent layer factorizes, and the distribution also follows the constraint specified by the graph. And finally, if we want to obtain the marginal distribution of the observed p variables, we need to marginalize out all the latent variables. Through this, we can see that this Bayesian pyramid induces a very flexible and complicated dependence model for the p variables. So, as I said before, identifiability is a fundamental property of a statistical model, but it can be challenging to study for latent variable models, and especially the complicated models in our case. In this work, we propose transparent identifiability conditions. these conditions only depend on the graphical matrices G themselves. Specifically, we need each GM to include 3 copies of identity submatrices IKM, and the remaining submatrix GM star can take an arbitrary form. Then the following quantities are identifiable up to a latent variable permutation within each layer. These quantities include the distribution of the deepest latent variable Z and the conditional distribution of all the other variables given their parents, and also all the graphical matrices themselves. They can be identified. So here I should mention that we consider all the latent variables in these middle layers to be binary for interpretability and for theory. A nice consequence of this identifiability theory is the posterior consistency of Bayesian estimators. Indeed, under suitable priors, the posterior would place increasing probability in an arbitrary small neighborhood of the true parameters. Such ability to reliably estimate the parameters is the key to interpreting the latent structure, and is also the key to use the learned structure in downstream analysis. And it is worth mentioning that our identifiability conditions are quite general, and it does not restrict the conditional probability table to take any specific parametric form. Here, for illustration purpose, we next will focus on the main effect models. And it is similar to the formulation of deep belief networks, because here we model the conditional distribution of each binary latent variable as a sigmoid function of the linear predictors, and the linear predictors are its parent variables. But the deep belief networks in machine learning literature, they don't consider the sparse connections between layers and didn't consider the identifiability issue. And it's worth pointing out that other more complicated models or more succinct models are possible. Not necessarily these main effects of parent variables are needed, but as long as the graphical constraints are followed, our identifiability theory equally applies. There are some interesting connections between our models and studies and some other existing works. In psychometrics, there have been a family of cognitive diagnostic models for diagnosing presence and absence of latent skills. But these models are usually confirmatory rather than fully exploratory here. Although there are some studies on identifiability, but the deep multi-layer latent structures have not been considered. On the other hand, in machine learning literature, there have been some very popular and useful methods, such as deep belief networks, latent tree models. They are very popular and useful in various prediction tasks, but the identifiability issue is typically ignored. Now that we have an understanding of what model is identifiable, the second question is the estimation method, how to infer latent structure. As an illustration, we next focus on the two-latent-layer Bayesian pyramid with k binary latent variables in the middle and a deep latent variable Z with B categories in the top. Specifically, as mentioned before, we specify the conditional distribution of the YJs to be multinomial logit. And inside the logit, we have the linear predictors. And now an important fact to note is that the graphical matrix G plays an important role in specifying these conditional distributions. We can see that the entries of G directly enter this distribution. So in terms of estimation, we not only need to estimate these continuous beta coefficients, but also its underlying sparsity structure, which are these G indicators. Also, the alpha case, the individual latent indicators of subjects, also need to be estimated. So to complete model specification, we just use a latent class model to model the distribution of these k binary variables, with the Z serving as the deep latent class. This specific parametric form of the main effect-based models actually allows for relaxed identifiability notion and conditions. Specifically, here we can lift the previous requirement of G containing 3 identity submatrices. Rather, here we only require G to contain 3 submatrices in this form. The diagonal entries are ones, but any off-diagonal entry is free to be either 1 or 0. Also, suppose that the number of binary latent variables in the middle layer is not too small with regard to the number of deep latent categories B. Then all the latent structures and model parameters are generically identifiable. Here, generic identifiability means that the parameters are identifiable almost everywhere in the parameter space, excluding only a Lebesgue measure 0 set. So we can see that this identifiability notion is quite useful and practical in real applications. So we adopt a Bayesian inference procedure for estimation of the latent structure. Our prior specifications are as follows. First, consider the case where we know the number of binary latent variable K. In this case, we specify a joint prior for the sparsity indicators G and the continuous beta coefficients. This is a spike and slab representation where the slab variance sigma further is modeled using the inverse gamma. So in practice, we usually do not know how many binary latent variables to use. Therefore, we adopt a cumulative shrinkage process prior recently proposed Bayesian non-parametric Bayesian method. In this method, we specify an upper bound, K upper, for the number of binary latent traits. And the variance for the beta coefficients still follows a spike and slab representation, where the probability that alpha K belongs to a redundant spike component. The pi K probability is a sum of a stick breaking process. So the nice formulations allows for efficient deep sampling updates. For fixed K, we just use a Gibbs sampler by employing the polygamma data augmentation for logistic regression. And we also employ the auxiliary variable method for multinomial logic models. For unknown K, under the cumulative shrinkage process prior, we also develop Gibbs updates. And this is possible thanks to the stick breaking representation introduced before. Under the CSP prior, since the pi K has interpretation of the probability that the case latent variable is redundant. So actually we have an analytic form for the posterior mean of K star. This posterior mean depends on the pi case. So thus far, we have described an entire procedure for inferring the latent structure and model parameters fully exploratorily from the observed data. Here are some simulation results. In the simulation, we specify the true number of binary latent traits to be 4, and we specify the number of categories for each observed variable also to be 4. On the rightmost plot is the true coefficient matrix, the beta. And note that the sparsity pattern of this beta matrix actually exactly is the G matrix, the graphical matrix. We can see that there are 3 identity submatrices here, so our identifiability conditions are satisfied in this case. Indeed, for sample size as small as 500, when over-specifying the number of binary latent traits to be 7, the method is able to identify the sparsity structure of this matrix. And for sample size 2000, we can see that the estimation of the beta coefficients themselves are already very accurate. We also perform simulation studies for various sample sizes to assess the posterior consistency. Here we plot the mean estimation errors of the graphical matrices for different sample sizes from 250 to 2000. We can see that for sample size as small as 750, the estimation of G across all the 50 simulation replications is very accurate. And for the continuous parameters in the model, the beta coefficients and the deeper eta coefficients, we also plot its RMSE, root mean squared errors versus sample size, and we see it decreases as sample size increases. So actually, this empirically validates our posterior consistency and shows the good performance of the Bayesian procedure. We apply the method also to a real data set. So some background is as follows. In genes, there are two regions, the introns, which are the regions removed during RNA transcription. And there are exons, which are regions used to generate messenger RNA. The junctions between these two regions are called splice junctions. They have three types, the EI type, IE type, and the neither type. The splice dataset is about the splice junctions. Here we observe some 3,000 nucleotide sequences, so N equals 3,175. Each sequence has length 60. And at each locus of the sequence, we observe either A, C, G, or T, 4 categories. This table summarizes the real data. So in the last column are the 60-dimensional multivariate categorical data. And in the second column here are additional sequence type information, EI, IE, or N, provided by domain experts. Here we want to assess our method's performance in learning useful latent representations. So we hold out this type information, but only use the sequence data information in the last column. That is, we perform unsupervised learning. We apply our Bayesian procedure with a cumulative shrinkage process prior, and we obtain 5 binary latent attributes. Here's an overview of our data analysis. The first plot is the element-wise posterior mode of the graphical matrix. There are some interesting patterns here, but what is more interesting actually is the lower dimensional latent representations learned for the some 3,000 nucleotide sequences in B and C. So let's look at these more closely. Visual inspection can already show that there are very clear distinctions between the latent features learned for the 3 types of nucleotide sequences, EI, IE, and N. Note that the sequence type information on the right, they're held out during our estimation. Indeed, if we use an interpretable machine learning classification approach to map A and Z to the type, actually this method outputs very simple rules. So these simple rules deterministically map the features in A and Z to the sequence type. If we plot the confusion matrix of this classification, we can see that the classification accuracy for all the 3 types exceeds 95%. This even matches what is given by fine-tuned convolutional neural networks. To summarize, in this work, we have addressed the theoretical identifiability issue. We developed a general theory to identify potentially deep latent structures underlying multivariate categorical data. The identifiability ensures Bayesian posterior consistency, and they provide reassurance that one can reliably and reproducibly learn the latent structures. On the methodology side, we propose a Bayesian procedure to infer the entire latent structure and model parameters exploratory. Our simulations show the computational performance of the method is very good, and it actually also corroborates the identifiability theory. The proposed approach is also able to identify meaningful and useful latent structure in the real data. You can find more details in our archive preprint, and thank you for your attention.